want to start again with the soft k-mean clustering problem, the algorithm. Showing that we can improve it to also solve some other problems. Let us remind what we are talking about. So, we have a set D of elements. These elements are possibly in a high-dimensional space. And in particular, we have this number of elements. And we want to approximate them with a small set of vectors, a set of k vectors. Of course, each of them being in the same space, so that we minimize the distance, the sum of the distances, let's write it as a norm, between, for all documents in, well, let us index the documents I from 1 to m, between the ith element of D and the closest element, the closest vector move, where the closest vector is such that, of course, the index is chosen so that it minimizes for all possible elements the distance between di and the generic element of J. Okay, this is all the definition that we need to work. I keep writing this every time, but I want to remember all the names, of course. This is important. Now, last time I left you with this particular algorithm, the one that fixes, initializes every vector, every cluster representative with some random position. We can have many different ways of computing this random position. Then, we repeat the same process of finding, taking one element, so we choose one index inside here. At this point, of course, the corresponding index for mu is the closest one. Well, let's say this. Okay, so let me call this L. Okay, so we are in the usual situation. We have some mu here and there. So what we repeat is this. We choose one particular element, say this. We find, so I, this is the element Gi. We find the value for L, so that mu L is the closest to the I. In this case, this will be our mu L. But what we do is we slightly move this vector towards this document. Okay, so we update the position of mu L by adding to it a small amount of the difference between di and mu. Okay. This means move mu L towards di. Of course, with eta conveniently placed between 0 and 1, possibly by some experiment. And what we get by this simple algorithm is that these mu L's tend to move towards distinct clusters. You can take the code that we wrote last Tuesday. By the way, I have put it on the web page. That was for the hard clustering procedure. Okay, but you can easily modify it to use it with this soft clustering procedure and see what happens when you keep iterating. How long should we repeat this? Of course, we don't have precise criteria for that. We can, well, simply repeat it as much as we can. Or, let's say, the only indication that we can give is repeat until satisfied. Okay, meaning that these mu L's are never going to stop. Every time they will be pulled here and there by the elements even of the cluster they end up within. I mean, this mu L is going to move iteration after iteration. Every time this choice falls in this cloud of points, this element will move here and there within the cloud. It will never stop. Of course, we can always say when the last n moves, where n is some large number, did not exceed some specified parameter, so if the don't move that much, then we can stop. Or yes, actually there is very little that we can say in this case. Well, actually, as I said last time, we are we are interested in possibly having this parameter eta to become smaller and smaller as time proceeds. So make it become eta of t, where t is something that is initialized here and which is increased every time. So that eta of t should be something that becomes smaller as t grows. And it could be something like this, some initial value eta 0 times something that moves from 1 and decreases as time goes on, for example, e power minus t squared. For t equal to 0, eta is equal to eta 0. As t grows, this becomes smaller. And of course it becomes exponentially smaller. So maybe we want to reduce the effect of t by adding another constant, let's call it sigma, down here. Okay, the effect is that we are having some, so if this is t and this is eta, we have something that starts from eta 0 and depending on the value of sigma decreases more or less rapidly. This is for a large sigma and this is for a small sigma. Okay, so by playing on some parameters we can find the ideal reduction plan for our coefficient eta. Is that okay up to here? Okay, now why do we need clustering? As I said, the main goal of clustering is this. We have a very large number of elements M. We reduce our set by considering only k different prototypes for those elements. So instead of considering 1000 white dots, we can just consider 3 blue dots, as long as the 3 blue dots are placed in convenient positions so that they represent the documents. In fact, this formula actually means okay, the different prototypes for the different clusters represent my documents well. So there is no document that is too far from every move. Or if there are documents that are very far, they are few with respect to M. Okay, actually, anyway, what's important is that we reduce the complexity of our set from M to K. In another sense, I'm saying that rather than considering 1000 different elements, I'm just considering k different types of elements, k different classes of elements. There is another number here that we would like to reduce. Okay, the first large number is this. But the other very large number, at least in some situations, is n. The dimensionality of the space where our elements reside. In many cases, this number is very large. For example, I made the example of documents Document is the main reason why the set is called D. In fact, from time to time I call the elements documents. Why? Because one of the main examples for this kind of algorithms is when these are documents, for example, web pages, published articles, and so on. And this N is the set of all possible terms that can appear in those documents. We already saw the TF-IDF representation, where every document is represented as a vector of real numbers. How many real numbers? As many as there are terms in our collection of documents. So in that case, this value for n can easily become tens of thousands. Okay, the typical human language has between the tens and the hundreds of thousands of words. Of course, not all those words are important. Some can be removed. We spoke about stop words. We can remove them. Of course, but stop words are very few in the language. They are very used, but there are very few terms that are repeated and repeated and repeated. On the other hand, many terms that are uncommon are very important in terms of representing a document, exactly for that reason, because they are uncommon. So they can easily be used to classify some document. So it is true that there are few terms that are very used, and lots of terms in a human language that are almost never used. But those many terms that are almost never used are very important for analyzing documents. So n, for that reason, can be very large. It means that the average document in D will be represented by a vector, by a very sparse vector with many zeros, but with ones with some elements different from zero that can appear in any position. Well, the problem is this: if n is large, how can we hope to represent our set of elements, of documents, in some convenient two-dimensional space such as a blackboard? I mean, I would like to use this white space, this black space, and say, okay, my documents are represented like this, where this is the region where, who knows, politics is represented, while down here you find the documents that speak about cars, and here something about programming. And you see a particular document can be found here. In fact, it is a paper about programming embedded systems for cars. Okay, I would like to be able to represent my documents in a small dimensional space, 2, at most 3, but 2 is better, so that the position of my elements in this space is significant for me, can be interpreted by me somehow. Okay, and the problem is that n is not 2. Okay, if I had to represent this set of documents in the original space, I would need n perpendicular axes. We don't have enough physical dimensions to do that. So, the other problem that we need to consider in order to be able to represent our documents is the problem of dimensionality reduction. Okay, so what we have seen up to now is the reduction of the number of elements. Now we will consider the reduction of the dimensions of the space where the elements are represented. And, well, the first way that we have to make such reduction can start from this algorithm. You see, here we are associating every element of our original set D to a small number of clusters. Well, so, say, how can we draw that? Let's say, the idea is this. Suppose that our vectors move, rather than having just one index, j. You see, if we have just one index, when we set indices in a set, we are implicitly ordering its elements. In fact, I am listing these vectors mu from mu1 to mu k. Okay, they are k elements, and I am listing from the first to the last. Actually, this algorithm is insensitive to the particular order of the mu vectors. I mean that if I take these vectors and I mix them, I permute their indices. Okay, I change the indices so that mu1 becomes the third vector, mu2 becomes the last vector, and so on. Actually, the result remains exactly the same. If I permute the vectors, nothing changes, and I mean, if I have this cloud of points, the fact that this particular representative is called mu3 or is called mu5 does not change anything on the fact that this vector will be moved to some direction which is independent from this number, of course. This number is only a way that we have to keep track of all the vectors. Okay, so suppose that we do this. Rather than using only one index, we use two indices. Sorry, I have to remove some signs here and there. Say mu1, 1 up to mu1. Of course, I need more letters to do that, and that's always a problem. Okay, this is the number of columns, so okay, let me call this C. I don't like C because it's cluster. Okay, let's say K1. Okay, this is K. I already used the L there. And okay, let's go. This is P. Mu Q1 up to QP. Let's say this is Q and this is P. Otherwise, I would keep mixing them. PQ is better, it's clear. Okay, what I'm saying is, suppose that we index our clusters, our mu, with two indices. Rather than putting them on a line from 1 to k, we decide to represent them with two indices as if they were the elements of a matrix. So that the old k is actually the product PQ. Okay. If we call k the number, the total number of course these are vectors. Each of them is a vector. Rather than okay, let's say the number of elements is the same, but rather than calling them with one element, we call them with two. So that, okay, here we just need to change a little this the choice of the index, but it's only a matter of choosing two numbers, two indices instead of one. So what I am actually using is two indices, let's call them L1 and L2, so that L1 is from 1 to P and L2 is from 1 to Q. Oh, sorry, here I need J1 and J2. J1, J2. Okay, what I'm saying here is that I haven't been changing anything important. Only, let's say, the names of the cluster representatives. Is it clear to everybody? Everything works as before. Only that, instead of listing my moves as they were in a line from 1 to k, I represent my move as if they were in a grid with p rows and q columns. Which is what I'm actually going to do now. P and 1, 2 to Q. Okay. So what I had before was if I had to write some computer program to compute this k-means and stuff, I would have placed every representative vector mu in an array, a list, indexed by just one number, which is what we have done last Tuesday. Vectors were in a linear list, and they were listed from 1 to k, well, actually from 0 to k minus 1. Okay, now let's move to this way of placing our representative, so that move 1, 1 is here, move 1, 2, and so on, until move 1, q. Here we have move p1 until move pq. The generic element here can be called, so if it is in row L1 and in column L2, it's move L1, L2. Okay. I repeat once again, from the point of view of the algorithm execution, nothing changes. The fact that we put our vectors move in a line, in a grid, or in any other data structure you choose, does not change anything. So why have I done this? Because the next thing we can do is the following. Suppose that we have run this procedure until satisfied. Okay, so we have done this iteration a lot of times, so that each of these vectors are actually placed somewhere in our n-dimensional space. Each of these vectors is an n-dimensional vector. Okay. So let's forget about before. Let's say we have lots of points here and there. Suppose that P is 3 and Q is 3, so we have actually 9 vectors to place. So we have move 1, 1, move 1, 2, 1 here, move 1, 3 here, move 2, 1, 1 here, move 2, 2 here, move 2, 3, move 3, 1, move 3, 2, and move 3, 3. Okay, suppose that after running this algorithm, every move fell inside some of the many clouds. Here, of course, we are in n dimensions. Even though they appear to be 2, suppose that this is a very complex dimensional space. Okay, just to be fair, this centroid should be here because it's pulled by both of these clusters. Okay, so move 1, 1 is here. Again, I repeat, nothing changes. The fact that we use the 2 indices rather than 1 to represent our centroids does not change anything in the algorithm. The centroids would occupy exactly the same position independently on our particular ordering of the vectors. Now, okay, so let me reduce this matrix to a 3 by 3 matrix. Okay. Now, as you know, let me take another color. The position of the centroids in the n-dimensional space induces a separation of domains called the Varanoy diagram, where let's see, it's here like this, this. Okay, something like this. Okay, where these lines represent the border of the domain of each of these vectors mu. Okay, every point that falls in here belongs to vector mu2, 1, because mu2, 1 is the closest representative to all points within these orange borders in this zone. Okay? Okay, now let's take all the original points that belong to mu1, 1, and let's represent it, let's put them in this square. Okay, suppose that these are D1, D3, D15 here. Okay, let's list them in the first rectangle. Maybe D2 was here in mu3, 1. Okay, let's write it down in this place. If D7 is here in mu2, 1, okay, not quite often, but always 1. Let's say D8 is in mu2, 2, okay. D8 will appear here along with all the documents that appear in this particular region. So let's take all documents and put them in the entry of this 3 by 3 table that corresponds to their representative vector. Okay. Does this give us more information than before? Actually, no. What I'm doing here is, okay, I take all the elements that belong to the same cluster and I list them in the same place of the table. Okay. Now, the important part is this. Okay, so let's see. Okay. The next step will be this. Now, as I repeated at least 5 times, okay, but let me repeat it the 6th time. these centroids, these, the position of these representative vectors, do not depend on their indices. Now, let's make them dependent on the indices. My purpose is that representatives that have similar sets of indices, so that are close together in this table, should move together in this algorithm, so that they tend to occupy clouds of points that are close to each other. So up to now, every cluster representative was treated separately from all the others. Now, what I want to say is that, for example, if in this algorithm I find that I have to move 1, 1 in some direction towards some document, then a small movement in the same direction should be applied to those vectors that have similar indices. For example, to vectors move 2, 1 and move 1, 2. To the vectors that have the closest, that are closer to this one in this table. So the main idea is that if move 1, 1 falls here, then also move 2, 1, okay, move 1, 1 is the vector that controls what goes in this square. Move 1, 2 is the vector that controls what goes in this square. Move 2, 1 is the vector that controls what goes in this square. So, if move 1, 1 controls this cluster, well, actually, I would like that also move 2, 1, which occupies a square which is close to this one, goes to control some cluster that is close to this one. So every time I move 1, 1 in direction, I also want to move 2, 1 in the same direction, so that hopefully it will control a closer square, and the other representatives move far away. So representatives that control squares that are close to each other should end up controlling clusters that are close to each other. This is the main idea. And the way we do it is something like this. Okay, here we found the indices of the closest representative to the point, and we moved it this way. Well, actually, what we can do is okay, of course we need to introduce another distance function. In this case, a distance between the squares of this matrix. Let's call it theta. Theta is a function that tells me, given two squares in this matrix, it tells me how far apart they are. Or better, how close they are. Okay. So given indices, let me find let's see. Okay, I have to use this, and let's go back to the general case where we have P rows and Q columns. What I want to find now is what I want to define now is a function that tells me how close these two squares are. And I suppose that this square is, of course, we always have the usual problem of letters. So let's say that this is let's say, okay, this is row R1 and column C1, and this is row R2 and column C2. So this is actually a function of 4 indices, R1, C1, R2, and C2. And okay, let me delete everything. So I need some proximity function between and I want this function to satisfy some properties. For example, I want to be 1 if I'm considering the distance between one square and itself. So 1 if R1 is equal to R2 and C1 is equal to C2. I want it to be 0 if two squares are too far apart. So if R1 C1 is far from R2 C2 and have some values in the middle for closed squares. Okay, so I want a function that goes from 1 to 0. It is 1 if it is considering the proximity between a square and itself, and reduces to 0 once some threshold distance is once the distance between the two squares is too large. Now, the only thing I have to do is modify this update rule. Instead of only moving the closest representative to a document, as I have done here, I do this. For all, let's say, index R from 1 to P and index C from 1 to Q. So for all vectors mu, I update the vector mu R C. Okay, instead of only updating the closest vector, I update all vectors. How? I always apply a difference in increment to the previous value, and the increment will be given by, okay, before I only had this eta value, okay, times the difference between the element di and the previous value of vector Rc. This was the previous update rule that was only applied to the vector L1 and L2. Well, here the increment will be proportional to this new function of proximity between the vector L1, L2, that is meaning the closest vector to di, and the generic vector Rc. Of course, once I have done this, I also increase the time. In this way, every time I choose one element of my original set, I find the closest representative, and I apply the update rule to all representatives with an increment that is proportional to to what? Actually, that is proportional to the proximity between the indices of the two representatives of that. So the main difficulty here when it comes to understanding what's happening is that here we have well, somehow two different spaces where we are representing things. We have the original n-dimensional space where elements reside, and where also the representatives mu reside, because every mu is always an Rn vector. But together with this, we also choose to place our representatives in a sort of two-dimensional space, in this case a discrete two-dimensional space, so that we can build a relationship between two representatives based on their on their representation on the two-dimensional grid. Okay, let's see an example. this is our usual n-dimensional space with all our elements di in it. And this is the collection of our PQ representatives. What I'm saying is this. Okay, each of these representatives is somewhere in the n-dimensional space. Okay, if this is, let's take the generic C. Okay, this square of this matrix is associated to the representative mu r c, which is a vector in the n-dimensional space. Each of these squares contains a vector in the n-dimensional space. Now, suppose that by executing this algorithm, we choose a document, for example, this one. Okay, this will be di, so that okay, once we have chosen di, we look for all representatives will be here in this space. We find the closest one, and let's call L1, L2 the row and column index of the closest representative, L1 and L2. Now, the next thing we do is, okay, we update these representatives. How do we update them? Okay, the closest representative will have this theta value equal to 1. Right? So it will move towards document di. Next, okay, what I mean is that not only this representative will move, but also representatives that are associated to nearby squares. Suppose that this square, meaning L1, L2 plus 1, okay, same row, one more column, it's very close to this, is associated to a completely different representative, of course. Okay, also this representative will be slightly moved towards the same document. Also this element, which may be, for example, this, will be slightly moved toward that document. And so this and this. This square is a little farther, okay, it's a little less closer. Suppose that it corresponds to this representative, okay. This representative will also be moved towards the document, but of a much smaller amount. So, once we have found the document, and we have found the closest representative in this space, which is, for example, this, the representative associated with this square, this representative will be moved by a large amount, but also the representatives associated to nearby cells will move of a smaller amount towards the same document. This will have the effect of making representatives associated to nearby cells, nearby squares, to move to close regions in the original n-dimensional space. The effect is that the representative associated to this square and the representative associated to this square will most probably represent clusters that are close together in the n-dimensional space. Okay, so what we have added here is this notion of proximity of vectors in this two-dimensional grid. While in the previous case, in the K-means clustering classical example, we only consider proximity in the Rn space, so Euclidean distance in this large dimensional space. In this case, we have two possible relationships. One is the distance in the high dimensional space, and one is the proximity of cluster representatives in this two-dimensional space. This algorithm is called self-organizing map, abbreviated in SOM, SOM, or also Cohonen map by the name of its original proposer. There is another way, maybe yes. Maybe we can better see the effect of this algorithm by considering this case. Suppose that the idea is that suppose that we have a set of clusters. Let me make nine of them as usual. The idea is this: not only we have nine centroids as before, but somehow these centroids are connected in a grid. I have lost, okay. In a 3x3 grid. And when I, for example, here, I choose this document, and this document pulls the closest representative in this direction, actually also the representatives that are, so somehow the movement will propagate along this grid as if they were some springs, okay, so that also these elements will tend to move in the same direction. Of course, this element now will be slightly moved in that direction, but once we pull this, it will also be pulled in that direction. So the net effect is that this grid will open up you see, so that two representatives that are connected by the grid will end up in similar places of the original space. Of course, it's not that easy. Here we can see the effect in 2 dimensions, but of course, when we go to many more dimensions, it will become much more difficult. But anyway, okay, we get a final effect which is exactly the same as the k-means algorithm, with the additional result that representatives with similar indices are probably close together also in the n-dimensional space. So now, for example, one thing that we usually do with self-organizing maps is this. Suppose that these are documents, okay? So web pages, for example. Once we have computed the k-means algorithm, what we actually get is a distribution of web pages in a P by Q matrix. So that, for example, who knows, okay, I mean, every page will be associated to one of these cells, and in particular it will be associated to the cell having the representative that is closest to the original document. Let's see. Let's see. The generic page DI belonging to the set D will be associated to cell IJ, no IJ, RC, where RC is the usual row and column that minimizes this distance. So, given the document, we find the cell corresponding to the cluster representative which is closest, so that document dy can be actually associated to this cell. Now, suppose that we have done this for all documents in our set. So we have actually taken our documents one by one and decided in what cell it must be put. We have distributed documents along these cells. Documents that are very similar are associated to the same representative, so they will fall in the same cell. This is the essence of clustering. What we get more, the additional effect that we get here, is that even documents that are not that similar and that belong to different clusters will fall, if they fall into similar clusters, they will be in nearby cells. So that if this cluster, what we can hope to get with this algorithm is that if this cluster represents, programming in Java, maybe the cluster here will represent programming in C. Why? Because, okay, maybe documents that refer to programming in Java contain slightly different terms from documents that refer to programming in C. For example, documents about Java will never discuss memory allocation because it's automatic in Java. While, of course, when you speak about C or C++, you also have to discuss details on freeing memory and so on. There are some differences so that documents about Java and about C can fall in different clusters. But if you look at their position, if you were able to look at their position in the n-dimensional space, which you can't do because we are limited to 3 dimensions, but you will find that Java documents and C documents tend to be in occupied to close regions of this n-dimensional space. By virtue of this method that moves similar centroids, closed centroids, well, documents about C will fall in a nearby cell. Well, of course, documents that speak about other issues will fall in other regions of this matrix. The idea is that once you have collected all documents, it should be easier for you to see what these documents are about. For example, if you want to characterize the documents that are within this cell, you will probably try to find the most common term in these pages. Of course, the most common term will probably be something like they or and, but by removing stopwords, by considering, by weighting all terms with their inverse document frequency, for example, you should be able to find that here the term Java is the most frequent one, while here you find C++. Or if you look at these two cells combined, you find that the most shared term between here and here is programming, and so on. You can build a representation where different terms, representative terms of pages, are placed on clusters, and so that you can actually have a representation of how your space is, your original space is structured. You can do it, okay, by so, of course, the main goal of this kind of algorithm is visual representation of information. You get it when you actually want to place things on a 2x2, on a two-dimensional grid. Actually, this division into squares is not the most popular. What's it? Well, let me generalize this algorithm just a little. For example, rather than placing things in a rectangular grid, what is usually done is that we place it in a sort of honeycomb space. Oh, let's do it like this. And so on. What is the advantage of placing things on a hexagonal structure rather than a rectangular grid? Well, the main advantage is that, consider this cell. It has many neighbors having exactly the same distance, and somehow the hexagon better approximates a circle, so that you have things all around it somehow. This structure, okay, we can call it, for example, honeycomb structure. It's the structure of cells that bees build in their nests, okay, or hexagonal. Grid. Okay, in this case, well, we can also find rows and columns here, okay. This is the row 1, row 2, row 3. But actually column 1 is, okay, this one. Column 2 is this one, and so on. And of course the proximity function between column 2 and column 2 is a bit more difficult because it depends on the parity of R, for example. C equal 5. So that, for example, this cell, which is cell 2, 3, is close to cells, okay, 2, 2, 2, 4, 1, 3, 1, 4, 3, 3, and 3, 4. it's a little more difficult to find the neighborhood relationship in this case. But again, the only difficulty amounts at finding this neighborhood relationship. Once you have defined this theta function, the algorithm is exactly this one. Actually, if you have to well, this algorithm is usually presented in a more general way, where you're not making any assumption on the indices of your weight vectors, of your representatives. So in general, now after 2 hours of changing indices, let's go back to a representation where you are just listing your representatives from 1 to k. At this point, for example, in this structure, you can place your vectors like this: move 1, move 2, move 3, move 4, move 5, then move 6 here, move 7, move 8, and so on. Okay, so let's just give one index to every vector move. Of course, all we have to do is, again, define our function theta between two generic indices L1 and L2. Once I have done this, we can write here like this. So that move J is incremented depending on its relationship with the index L, like this. So let us definitely separate the two-dimensional representation of our representatives or clusters from the n-dimensional structure of our space. The two-dimensional representation is somehow stored in this function theta, so that given the indices of two representatives, it says how close they are in the grid that I have chosen. Okay, so here we can still use one to simplify things. Here we can still use one index to list our representatives, and the algorithm becomes simpler to read and to write. And the two-dimensional structure is in our mind, of course, and in this function. So, let's say, for example, in this, suppose that we have a P by Q hexagonal grid. And suppose that we number our representatives like this: 1, 2, 3, 4, 5 up to Q. Then the second row will have indices from Q plus 1 up to 2Q. The third row will be 2Q plus 1 up to 3Q, and so on. The last row will have indices R minus 1Q plus 1 up to RQ. Sorry, this is P. P minus 1Q plus 1. P minus 1Q plus 1 up to PQ. Okay, suppose that we just number our vectors like this. Suppose now that given one cell of index, no, sorry, we have no rows and columns. Given this cell, I want that theta between this cell and itself is of course 1. Theta between this cell and the 6 surrounding cells is 1/2. Theta between this cell and all other cells is 0. Okay, suppose that I want to build this theta function. So, what's the generic theta between indices A, B, C, D, between index L and index J? Of course, it will be 1 if L and J are the same index. When is it going to be 1/2? Well, it's going to be 1/2 when it is one of the, it's the previous or the following cell, but actually it depends on many things. For example, if we are here in the border, the previous cell will be here. So we should avoid this. So we have to take into account a series of border effects that make it a little more difficult. What we do usually is, okay, suppose that we want to define theta between L and J in a sort of Python notation. Well, let's compute what is the row and column of each of the two elements. So the row corresponding to element L, okay. The other problem is that here we are based on 1. Things would work much better if everything started from 0, of course. Okay, it's too late for that. So the row corresponding to element L will be L minus 1 divided by the number of rows P plus 1. Okay, so values from 1 to Q will give 1, values from Q plus 1 to 2Q will give 2, and so on. For the same reason, the column corresponding to index L will be L minus 1 modulo P plus 1. Okay, I always subtract 1 to go to a 0-based number, and then finally I add 1 to go back to a this.
It's not divided by Q.
Divided by Q, you're perfectly right. Here and also here. Thanks. So, and the same, of course, the row corresponding to the element J will be J minus 1 divided by Q plus 1, and Cj is J minus 1 modulo Q plus 1. And now, the only thing that we have to consider is, well, of course, even before computing this, if L is equal to J, we directly return 1. Okay, even before computing this. And then we need to see some relationships between rows and columns to decide if the proximity should be 1/2 or 0. So, if the two elements belong to the same row, L is equal to Rj, then if the column of J is equal to the column of L minus 1, or the column of J is equal to the column of L plus 1, then we return 1/2. Okay, 1/5. Else, we return 0. Okay, if we are inside this if. Otherwise, okay, it's a bit longer than I hoped to do. I wanted to make a very simple toy example, but it seems that we have lots of conditions to consider. Otherwise, of course, if we need to check the row index, it must be on the row above or below. So if the two row indices are too far apart, more than 1, we return 0. Otherwise, we have to check that the two column indices are the one before or the one after. Okay. But anyway, all the actual geometric layout of our grid will be confined, will be limited to this function. Everything else will be completely oblivious of how we have organized our objects. The only place where the information is needed is here, where we use the theta function. Okay, so maybe tomorrow we can have a look at some code about this, so that we also see some visual representation. And okay, so my goal for tomorrow will be okay, find some interesting data set. In this case, of course, we cannot generate it by ourselves because it will have no meaning. So I'll try to find some good data set and try to apply this procedure and see what are the results. So tomorrow you will see some ways to actually use these self-organizing maps. Okay, it's all for today. Questions? Observations?
About the randomization of the mosaic, we
Yes.
have to do something more strict because of this disposition, so that we put the one cell and the other cell adjacent is not far away in the real. It will convert.
It's not that important. First, you see, it's difficult to do it because here you have a two-dimensional disposition. So moving to n dimensions means that okay, nearby vectors should be close, but in what direction? You have n possible directions here, so it's very complex. Second, you have to consider that even if you start from far away, but the farthest is moved from D, the largest is this difference. So the idea is that if you have, if these are two moves corresponding to closed cells, and this is pulled here in this direction, this one will have a larger pull because of the larger difference here. So they will actually tend anyway, and even not so slowly, to nearby positions. Anyway, yes, we need to experiment with that. But again, okay, it's difficult to put this information into this randomness.
To place eta, for instance, to 1 at the beginning, and then you move it towards 0. You can use the full strength eta in a sense.
Oh yes, in fact. So the idea is that in the initial steps you need to shake everything as much as you can. You're right. So eta will start rather large. Okay, anyway, tomorrow we can test it.